Our first objective is to be able to apply notation describing the infinite behavior of a function. Specifically, we are going to be looking at rational functions. A rational function is simply a polynomial divided by a polynomial, one polynomial on top of another polynomial. We have some notation in this table that we're going to be applying to these rational functions. The first set of notation, as x approaches c from the right, means that we will be going closer and closer to the x value of c coming in from the right side. Similarly, if we see this little minus sign up, it kind of looks like an exponent. That means we are approaching the value from the left side. The last two notations we have are for when we are approaching positive infinity and for when we are approaching negative infinity. And those mean respectively when x gets very, very big and when x gets very, very small. So in example 1, we have the graph of f of x equal to x minus 1 divided by x minus 3. That graph is right here, and we want to answer these four statements. The first of which is asking us, as x goes to positive infinity, what is f of x approaching? So as x goes to positive infinity means that on the graph has two pieces. It has this piece on the left, and then it has this piece on the right. If I want to approach positive infinity, I'm going to get on the piece on the right because I want to go towards x values that go towards positive infinity. So on that piece on the right, if we get on that piece, and as we move towards the right, so I'm moving towards the right, I'm interested in what is the function doing? What is the y value approaching? And it looks like the graph is leveling out at this y value of 1. So as x approaches positive infinity, the function f of x approaches 1. In other words, what we are saying is that as x gets very large, as the graph goes off to the right, y gets closer to 1. So the graph levels out at y is equal to 1. That is what that first statement is saying. The next thing we want to look at is what happens as x gets very, very small, as x approaches negative infinity. So this time I'm going to get on the left piece of the graph, and I'm going to approach negative infinity. So I'm looking at the graph as we go off to the left. Well, as we go off to the left, the y values again appear to be approaching a positive 1, because this graph is leveling out here as we approach x values near negative infinity. So as x approaches negative infinity, f of x also approaches positive 1. In other words, what we are saying there is that as x gets very small, as the graph goes off to the left, y gets closer and closer to positive 1. The next thing we want to look at is what's happening as x approaches 3 from the left. So first, let's just talk about what's happening at 3. If we look at this function, we learned back in Unit 1 how to find the domain of this function. We would take the denominator and set it not equal to 0. So x is not allowed to be 3. We can see on the graph here we have this vertical asymptote here at x is equal to 3 that is not in the domain. We'll talk more about what that asymptote means in a second. But what we want to look at here is what's happening to the function as we approach 3 from the right and as we approach 3 from the left. So to approach 3 from the right, I'm going to get on the right-hand side of the graph and I'm going to move in closer and closer to 3. So notice this time I am moving towards the x value of 3, but I do it on the graph. And as we approach 3 on the graph, we can see that these arrows are shooting up, and we can see that the function is approaching positive infinity. So in other words, what that statement tells us is that as x gets closer to 3 from the right side, the graph is shooting up to positive infinity. Similarly, let's look at what's happening as x approaches 3 from the left side. I'm going to get on the graph and this on the left side, and now I'm going to again approach 3. On the graph, I'm moving closer and closer to the x value of 3. And we can see that the graph is shooting down to negative infinity. You can see these orange arrows that point down as we approach 3 from the left. So what that means is that as x gets closer to 3 from the left side, the graph is shooting down to negative infinity. That's an interpretation of what this notation means here. So we should be able to look at graphs and see what they are doing as x gets very big as x gets very small, and as x approaches a vertical asymptote from either the left side or the right side. The next objective we have is for us to be able to identify vertical asymptotes and holes of a rational function. We begin with the definition of a vertical asymptote. A vertical asymptote is a line, x is equal to some number, where the graph is approaching either positive infinity or negative infinity from one side of that line. So for example, if x were approaching c from the right and the graph were shooting up to positive infinity, that would be an example of a vertical asymptote. The left side of the graph could be doing anything. It could be going down to negative infinity, or the left side of the graph could also be going up to positive infinity. If x approaches c from the left and the graph is going off to positive infinity, something like this graph is also having a vertical asymptote at x is equal to c. And then we have an example here of x approaching c from the right, the graph going down to negative infinity. Would look something like this. And if x is approaching c from the left and the graph is going down to negative infinity, that would look something like that. The next thing we're going to talk about is how do we find vertical asymptotes if we are just looking at the equation of the rational function and not a graph of it? Well, the blurb down at the bottom summarizes the process for us. Very important is that we have to make sure that the numerator and the denominator have no common factors before we go looking for vertical asymptotes. Once we have ensured that, then we will find numbers where the denominator is 0, but the numerator is not. While we're looking for vertical asymptotes, we will also be talking about finding holes. And to find holes, we have to find numbers where both the denominator and the numerator are 0 at the same time. So looking for vertical asymptotes and holes in these examples, I encourage you to start off by first factoring the numerator and the denominator if you can. So in example 2, our numerator is something that is linear, x minus 3, so that's not going to factor. But our denominator is quadratic and it can be factored. Because a is equal to 1 in this case, we can look for two numbers that multiply to negative 5 and add up to negative 4, and those numbers are negative 5 and positive 1. So I have the denominator factored. The numerator we can see is x minus 3. The first thing I want to point out is that the numerator and the denominator have no common factors. So nothing cancels out. Because it has no common factors, this rational function will have no holes because nothing is canceling. So as we have it written here, this is in simplest form. And it's in simplest form because there's nothing that can be canceled. We've already talked about how this has no holes because nothing is canceling out. To go on and find the vertical asymptotes, we take the denominator from simplest form and we set that denominator equal to 0. Because this is already factored, I'll simply set each factor equal to 0 to see that this quadratic has two vertical asymptotes, this rational function has two vertical asymptotes. It has a vertical asymptote at x is equal to 5, and it has a vertical asymptote at x is equal to negative 1. If I were to look at the graph of this rational function, we can see that graph off here to the right. We can see the vertical asymptotes that we're getting. We found vertical asymptotes at x is equal to 5, and we can see that vertical line right there coming in blue where the graph is splitting. And we found another vertical asymptote at x is equal to negative 1, and we can see that vertical line coming in there in green where the graph is also splitting. Notice that as x is approaching the vertical asymptote of negative 1 from the right, the graph is shooting off to positive infinity. As x is approaching the vertical asymptote of negative 1 from the left, the graph is shooting down to negative infinity. Let's go on to look at example 3. I'm going to begin by factoring the numerator and denominator if we can. The numerator is just a linear term. There's nothing to cancel there. The denominator can be factored. We can find two numbers that multiply to negative 3 and add up to negative 2, and those numbers are negative 3 and positive 1. Notice that in this case, we do have a common factor between the numerator and the denominator. The numerator and the denominator have a common factor of x minus 3. So to write this rational function in simplest terms, the x minus 3 cancels out, and we're just left with a 1 in the numerator and an x plus 1 in the denominator. So this is our rational function in simplest terms. In this example, something did cancel out, and so we will have a whole. And we find our whole by taking the common factor of x minus 3 and setting it equal to 0, and we get that x is equal to 3. So I know that the x-coordinate of the whole is 3. To find the y-coordinate of the whole, we plug 3 into the simplest terms. So I will be taking the expression of 1 over x plus 1 and plugging in 3. So I have 1 over 3 plus 1, which gives me 1/4. So I know the y-coordinate of the whole is 1/4. So this rational function has a whole at the point 3, 1/4. That whole is not included in the graph. It's an open circle because 3 is not in the domain of this function, since it would make the denominator equal to 0. So we found where the whole is. Let's go on to find where our vertical asymptote is. To find where the vertical asymptote is, we take the denominator from simplest terms, which is only x plus 1, and we set that equal to 0. And setting that equal to 0 in solving gives us a vertical asymptote of x is equal to -1. In our next example, there's nothing that we could factor in the numerator. The numerator is simply 8. And there's also nothing that we can factor in the denominator. The denominator of x squared plus 25 does not factor. So this is already in simplest terms. Nothing will cancel out for this rational function. And if nothing cancels out, that means that we have no wholes. So now to go on and find our vertical asymptotes, we take the denominator from simplest terms, which in this case is the original denominator, and we set it equal to 0. But this quadratic equation has no real solutions because we know that we do not take square roots of negative numbers. So I had moved the 25 over to the other side of the equation so I could square root. But I cannot square root because we don't take square roots of negative numbers. So this rational function has no vertical asymptotes. So not every rational function will have vertical asymptotes, and not every rational function will have wholes. Here's an example of a rational function that has no vertical asymptotes and no wholes. So we just looked at how to find vertical asymptotes versus wholes. Now we're going to look at how to find horizontal asymptotes. Horizontal asymptotes are lines. They have the form y is equal to some number. What the horizontal asymptote does is it describes the behavior of what the function is doing as x gets very big approaching positive infinity, or as x gets very small approaching negative infinity. So to put that in perspective, if you think back to this first example, we saw that as x got really big, the function approached positive 1, and that x got really small. As x approached negative infinity, the function was also approaching positive 1. So we would say that this function has a horizontal asymptote at y is equal to 1, because we can see that the graph is leveling out here at this horizontal line of y is equal to 1. So what we're going to talk about now is how do we look at just the equation of a rational function and determine whether or not it has a horizontal asymptote. And how we do that all depends on the degrees of the numerator and the denominator. So what I mean by that is you will be paying attention to the degree of this numerator, which is 1, and the degree of this denominator, which is 2. We'll be paying attention to the degrees of 2 in both the numerator and denominator in example 6, and the degrees of 3 and 2 in the numerator and denominator of example 7. And it matters where the degrees are, whether the top or the bottom. So to break this down, this example here just says that n is the degree of the numerator and m is the degree of the denominator. Number 1 tells us that if the numerator has a larger degree than the denominator, then there is no horizontal asymptote. We can apply that to example 7, because in example 7, the degree of the numerator is greater than the degree of the denominator. Because the degree of the numerator is greater than the degree of the denominator, example 7 has no horizontal asymptote. Please do not confuse that with a vertical asymptote. Example 7 would have a vertical asymptote. In fact, it would have 2 vertical asymptotes, because this denominator of x squared minus 9 can be equal to 0, and x is equal to 3, and x is equal to negative 3. And this was already in simple terms. So I could find the vertical asymptotes by just taking the denominator and setting it equal to 0. So it does have two VAs, but it has no HA. And that's coming from number 1. If the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. Number 2 tells us if the degree of the numerator is smaller than the degree of the denominator, then there is an HA of y is equal to 0, horizontal asymptote of f. So we can see that in example 5, the degree of the numerator is less than the degree of the denominator. Because in this case, the degree of the numerator is 1, and that is smaller than the degree of the denominator, which is 2. So when that is the case, the horizontal asymptote is simply the line y is equal to 0. And that's coming directly from number 2. Number 3 tells us if the degree of the numerator is equal to the degree of the denominator, then we take the ratio of the leading coefficients. And that's exactly what we have going on in number 6. In number 6, the degree of the numerator is 2, which is equal to the degree of the denominator, which is also 2. So how we find our horizontal asymptote, we always start with y equals, and this tells us to take the ratio of the leading coefficients. So what that means is I look at the leading coefficient in the numerator. In the numerator, the leading coefficient is 3 because that's what's in front of the term with the highest exponent. And I divide that by the leading coefficient in the denominator, which is 1 because that's the number in front of the term with the highest exponent. So we can see that the HA is simply y is equal to. So those are 3 examples of how to find horizontal asymptotes of functions. And under these functions, we can see the graphs here. Notice in the first graph, we do see that the graph is leveling out along the horizontal line of y is equal to 0. While in the second graph, we can see the graph is leveling out along the horizontal line of y is equal to 3. And in the last graph, we can see that the graph doesn't really level out anywhere. This graph shoots off that way, and this graph shoots off that way. So this one has no horizontal asymptote. In fact, what's happening in the last graph is a slant asymptote. The asymptote is not a flat horizontal line. It is rather a slanted line like this. This pink dashed line that I'm drawing in there describes what's happening there. And we will see examples of that in our last objective where we look at slant and nonlinear asymptotes. The last thing we are going to look at is finding the equation of a slant or an oblique asymptote. A rational function is only going to have a slant asymptote if the degree of the numerator is exactly 1 more than the degree of the denominator. That's the only time that a rational function will have a slant asymptote. And to find the equation of that slant asymptote, we have to do the division between the numerator and the denominator and figure out what our quotient is. The equation of y is equal to our quotient will be the equation of our slant asymptote. So for example, in number 8, we can see that the degree of the numerator is equal to 3, and the degree of the denominator is equal to 2. Because the degree of the numerator is exactly 1 more, if I take 2 and add 1, I get 3. Now I know that it has a slant asymptote, and to find the slant asymptote, we're going to actually do this division. So I've set up my long division. What we get at the top, the quotient, will be a part of our answer for our slant asymptote. So going through this division, I need to multiply x squared by 3x in order to get 3x cubed. So I have a 3x cubed down here minus 27x. I'll do my subtraction. This turns into a plus 27x. This is my remainder. And I'm not terribly concerned with my remainder because all I need is the quotient to write my slant asymptote, which will be the line y is equal to 3x. So this example here, this 3x cubed over x squared minus 9, that's the same example we were looking at in number 7. When I drew in this pink line, that is the slant asymptote. That is the equation of the line y is equal to 3x.